Hey, what's up, Heritage? This is Mr. Leong, and today I'm going to talk about quadratic functions, how to graph them, and talk about some unique features about them. So you can see here that I've got Desmos loaded up, and we're going to start, actually, let me just adjust some settings real quick. Just kind of make a scale of 1 on both axes. So let's start by looking at some graphs of functions that we already know of, linear functions. Right? So let's type a function f of x equals, right, I'm going to just use the mx plus b form, so maybe like 2x, let's not show that, 2x plus 5. Right? So normally, how would we go about graphing a function like this? Well, if you're doing it by hand, you would use a table of values. So Desmos, we can create a table of values. So let's just choose some simple values, 0, 1, 2, 3, 4. And then over here, we'll go ahead and start writing our function. So 2x, right? So what that does is it's doubling each of these x values. 2 becomes 4, 3 becomes 6, and then plus 5. So then it adds 5 more. So we'll look over here in our kind of graphing window, and now we can see we've got some points, and they all kind of line up pretty much perfectly with one another. And then now I'll go ahead and switch over here, and you can see that, really, we don't have just these 5 purple points. There's really hundreds, thousands. There's really an infinite number of points there that all kind of follow this linear pattern. Okay. Let me just make all the points the same color. If you want to get a better sense of what that kind of looks like, think of it like this, right? There's an infinite number of points, right, that all kind of fall on that path there, on that line. Okay, and we never draw a bunch of points, we just draw a line, because what we imagine is all those points just kind of blend in together to make the line. All right, so what we know is that the numbers, the coefficients in our function correspond to different features about its graph. Okay. So for instance, the plus 5, right, is related to the y-intercept, right? It tells us exactly where our line crosses the y-axis. And we can change that, right? If I make the function, say, I don't know, just plus 3, we'll have to change it here in the table of values, plus 3, okay? Now our line crosses at the third value on the y-axis. If we make it just say plus 1, right, that adjusts our line. Now it only crosses at y equals 1. Okay? So this is called the constant value in the function, and then it's related to the y-intercept. Okay? Now we also know that this other coefficient, the 2, right, is related to the slope or the steepness of this line. Right? So right now, to get from one point to the next, we would have to rise 2 spaces. Right? Rise 2 spaces, rise 2 spaces. But if I change my function so that that coefficient is a 3, now my line is steeper and I have to rise 3 spaces to get from one point to the next. And keep in mind, each point is separated by 1 horizontal unit. So up 3 over 1, up 3 over 1. Right? And then we can do unique things like use fractions. Right? So 3 halves. Right? So now I have to go up 3 over 2, right? Up 3 over 2, right? To get from this point to this point, right? 3 halves, okay? All right, so this is pretty much a review of linear functions, right? Linear functions have kind of this slope value, which determines the steepness of the line, and it has this constant value, which determines the y-intercept. What we're going to transition to now is quadratic functions. Okay? So quadratic functions, what they all have in common is they all have a second power x term, right? So an x squared. Okay? So let's explore a little bit what just kind of this very simple function looks like, x squared. Okay? So we'll go to our table of values and we'll go ahead and type x squared. And what happens is each of our x values is raised to the second power, right? 1 squared is 1, 2 squared is 4, 3 squared is 9, okay? And then we can come over here and look, and our points are not falling in a straight line anymore, right? They're kind of curving up. Kind of sort of reminds you of exponential functions. Right? Remember, exponential functions kind of curve or ramp up. So it'll be interesting to see what the points look like over here. Okay, so let's put some negative x values in our table. Okay, so let's include -1, -2, -3, -4. And so what you notice is that the squares of those numbers are still positive, right? When you square a number, you multiply it by itself. So in the case of a negative times a negative is a positive, right? So all of our y coordinates are positive. And what we end up here in the graph is a very unique shape. It looks sort of like a U, okay? We have a name for this shape. It's called a parabola. I'm trying to click on this here. All right, there we go. All right, so this is what pretty much the shape of any quadratic function looks like. It has this very distinct U shape, parabola. And there's one very special point on this parabola, which is this point right here, right? It's, in this case, it's the lowest point on the curve. All right, so I think what I want to do next is kind of talk about constants. Remember, in their linear function, right, the constant determine the y-intercept. So let's see if that's the case here. So let's, add a constant to this function, x squared plus 1. I'll have to change that in my table of values too. Okay. All right. So what happened there? Well, it looks like all the points just moved up one space, right? Go back here, right? These were the original points. Okay. And then when I add the +1, they all just move up 1. And our parabola now crosses at y = 1. If I make this constant +2 in the function, okay, now the points just move up even more. Okay, and it crosses the y-axis at y = 2. So it looks like in a quadratic function, the constant is pretty much playing the same role, right? It determines where the graph, in this case, our parabola or curve, hits the y-axis. Okay, so let's just do something like +5. All right, so now all the points are 5 units higher, and this point specifically is crossing the y-axis at 5, or hits the y-axis at 5. All right, so here's kind of a neat little thing that we can do in Desmos. Let's take that off, and let's just choose a variable there. All right, and then I can create a slider, and I can just change that variable. Actually, let me do this. X. Okay. So as I make that constant larger number, right, you can see all the points are moving up. I'll stop at 5, and then you can see that that vertex point, right, or the point where it crosses the y-axis is at 5. You can drag it to the left. Okay, so now we're using, negative constants. So I stopped at -4, and now what you see is all the points just shifted 4 spaces down, and in particular, our y-intercept is at -4. All right, so that's how constants, that's the role that constants play when we look at quadratic functions. Okay, close that off now. All right, so let's explore having a coefficient in front of our x squared term. So let's, let me just center this again. Let's put a simple coefficient like 1. Well, that didn't seem to do anything, right? Because basically what's happening is we're taking the square of these x values and then timesing by 1. But when you multiply by 1, the value doesn't change. So that's why our table of value didn't change, okay, whether the 1's there or it's not there, right? It's the same numbers, and our graph hasn't changed either. So let's try a larger coefficient like 2. Right, now the second column here changes and the graph changed a little bit too. So what changed? Well, here, these were the squares of everything. Right? This is 1 squared, this was 2 squared, this is 3 squared. But then I'm going to multiply those results by 2. So 4 times 2 will become 8, 9 times 2 will become 18, 16 times 2 will become 32. So now all these squared values are going to get doubled as well. So yeah, so the graph seems to stretch vertically a bit. It seems a little bit more narrower than it originally was. Okay, let's try 3. Okay, so here's all the squared values, right? 1, 4, 9, 16, they're all perfect squares. But now we're going to multiply those results by 3, and so they get even bigger, right? So the points now are even higher, which means our graph is stretching vertically. Let's try like a decimal value, 0.5. Okay. So in this case, the points are actually shrinking down. They're getting closer to the y-axis, right? Remember, this first point was, 1 squared is 1. Now it's only half as high. Right? 2 squared should be 4, but now the point is only half as high. 3 squared would have been 9, but now the point is at 4.5. It's half as high, right? So this coefficient here is either going to stretch the points higher or shrink the points lower. Okay, and we can even do some cool things like incorporate negatives, right? So what if I put a -1 there? So now what's happening is I'm taking all these squared values and then multiplying them by -1. And we know that multiplying by a negative is just going to make all those points kind of flip down to the bottom half of the coordinate plane. Right? So now our parabola is opening downwards as opposed to opening upwards. It's basically being flipped down. Right, and we can, we don't have to do -1. We can do -2, for instance. All right, so let's just kind of generalize now. And let's see, I will just type this as x, and then let's just use a placeholder here. I'll call it a. All right, so when a is 1, then our function is just 1x squared, and this is just kind of the basic parabola. We call it the parent function. It's the simplest parabola or quadratic function we can graph. And then as we make that coefficient a larger number, such as 3, okay, you saw those points, but we're kind of shifting up, right? And so that's stretching our parabola vertically. Okay, and we can drag this down, right? So as we make that a value smaller, the points are shrinking down closer and closer to the x-axis. Yep. And then at some point, right, we'll flip over to a negative coefficient, and then all the points flip down, right, on the other side of the coordinate plane. All right, and as we make that a bigger and bigger negative number, the points are stretching further and further down. Right? So -3, right, they're just stretching more and more. All right, so let's put the two pieces together now. Okay, so let's write a kind of generic quadratic function ax squared plus c. All right, and so let's just kind of go back to, I think I can just type it in here, 1 and 0. Okay, so that's our parent function, right? The vertex is at the origin, 0, 0, and it's not being stretched or shrunken or reflected in any way. All right, so so we know that the constant, right, that is just going to shift all the points up or down. Okay, so the whole parabola just moves up or down depending on that c value, that constant. And whatever it is, for instance, if I set it here at 2, that's going to be also the point where the parabola crosses the y-axis. It's the y-intercept. Okay. This a value, which is the coefficient in front of the x squared term, what that's going to do is it's going to stretch or shrink the parabola, right? It's going to stretch those points further and further away from the vertex up, or further and further away from the vertex down. Okay. All right. So that was just kind of a quick demonstration on how the constant is related to the graph of the parabola, and also how the coefficient on the squared term relates to the parabola. Okay. Thanks for watching.